This is MA189 Tensegrity Wing Project. I am the body sub-team lead, Tajay Singleton.
I'm the wing sub-team lead, Edgar Hernandez.
I'm the wind tunnel test team sub-team lead, Ernesto Gallard.
A background for our project. Our main goal is to eliminate control surfaces from the wings on current airplanes, such as ailerons, rudders, and elevators, which will cause drag, and replace them with a more uniform body, a morphing wing, which will allow for the increase of lift both during takeoff and flight, leading to a less fuel consumption, therefore less environmental emissions, and a more efficient airplane. This will be achieved with the introduction of a tensegrity structure, which is a skeletal member, whose members are allowed to deform and also recover due to the tension between them. The main objectives of the team are to design the wing and its control system for the morphing, as well as the skin that will be able to morph and recover with the wing, the creation of a body to house the wing for in-flight testing, and the validation of the two structures through wind tunnel simulations and various other computerized simulations. The sub-team breakdown are as follows. The body team, which is in charge of designing the body, and the electronics for the propulsion of the RC plane. The wing sub-team, which is in charge of the creation of the CADs for the wing, as well as its dimensions and the control surfaces for the inside, allowing for the morphing. And the wind tunnel, which once again will be the validation of the aerodynamic efficiency of both structures through 3D printing of downscaled models. The requirements for both the plane and the body are tabulated to ensure for a proper redesign during the designing procedure in order to increase performance. For the fall quarter, the team has worked towards the establishments of these needs and requirements, and during as well as research for the skin, and during the winter quarter, the team hopes to obtain more practical results through the construction of each individual member for the wing and the body, and their separate validations, which will then be integrated together and ultimately tested during a flight simulation. The current progress for the body team was a 3D CAD of the basic structure of the fuselage, whose main priority are to be able to house both the electronics and the inner structures of the wing, as well as meet certain requirements such as wing loading, which incorporates the mass of the airplane and the area of the wing, as well as material for the plane, which should be very, very light in order to ensure that not too much thrust is needed, and therefore we can use a smaller engine. The electronics for the body are tabulated as well to ensure that we have enough thrust to generate lift while maintaining a very small and efficient electronic circuit.
So far progress for the wing sub-team is we have completed our CAD of the assembly for the wing structure. As you can see from the images on the slide, each rib consists of a leading base and a trailing tip. Our goal is to have the wing tip to be able to rotate about 15 degrees from the horizontal from a 0-degree angle of attack. And we have also selected a pulley system in which the pulley will control the trailing tip to create a rotation. So far we have created a 3D printed prototype in which we will be using servos with a coupler connected to a D-shaft. This D-shaft will run through the entire wing and it'll rotate. Rotation in the counterclockwise direction will lift the trailing tip up, and rotation in the clockwise direction will bring the trailing tip down. This will help us determine whether or not the pulley system we have designed will be able to control the wing tip on demand. We have also completed research on the wing skin material. Our team has decided that as of right now, the best selection would be Pure Gum Rubber from Rubbercal, a company located in Fountain Valley. This rubber has a minimum thickness of 1/16 inches, which is ideal for our wing. It is also very flexible and elastic, as it has a minimum elongation of about 800%, so that it should not tear as the wing rotates. It'll also only cost about $132 for an entire sheet, which is more than enough we need. It'll provide us about 3 times the amount we need for the wings.
So the progress made by the wind tunnel test team this quarter was primarily running simulations on the wing that was designed by the wing team. We want to verify that it has aerodynamic properties that maximize the lift over drag ratio to improve the glide ratio, which is the distance traveled divided by the amount of descent of the airplane, which will ultimately improve fuel economy and the climb performance. So here is a simulation of the ANSYS simulation. And we ran simulations using ANSYS and SolidWorks to determine the lift and drag forces as well as their corresponding coefficients. We hope to maximize the lift, although with that comes the cost of increasing the drag as well. So if you go through the simulations, we actually discovered that the wing will have to morph in the positive and negative direction for the angle of attack. Due to the inconsistencies of the simulation, through SolidWorks and ANSYS, we need to verify them experimentally in the wind tunnel, and we are going to do that by printing various models of various 3D models of the airfoil with varying angles of attack.
So in conclusion, for fall of 2019, we have designed the RC plane body CAD, we have designed the wing assembly CAD, we selected the skin material, and we have 3D printed some of the CAD models that we are still going to test in the wind tunnel. Next quarter, we are going to begin the fabrication of the wing and the RC plane body. We will be testing the pulley tension system to ensure that it provides the amount of torque required for the wing, and we will begin conducting wind tunnel tests of the 3D printed airfoils.